Hello, this is Megan Adicary from Lab Section M01, and for my final lab, I chose to investigate the Red Bull Stratos jump. In the Red Bull Stratos jump, Felix Baumgartner flew up approximately 36,000 meters in a helium balloon into the sky and then jumped. His goal? To break the speed of sound, which he did. For this experiment, I tried to model his motion in VPython by applying physics concepts such as the momentum principle and the effects of drag on falling objects. The resulting model was able to mimic Baumgartner's fall, however very roughly. This was because there are many factors that affected the forces that were acting on him as he fell. Factors such as air density, drag coefficient, and even his body position as he fell contributed to the forces acting on him, yet they were really hard to approximate and model. Yet the resulting model was able to predict the general motion pretty fairly. So in order to model the motion, I had to find data which I could use to make my model and compare afterwards. Unfortunately, the data available only had a few data points. However, these were the most critical as they tell when and where Baumgartner reached the speed of sound, surpassed it, and how far he fell before his parachute deployed. Since Baumgartner's jump was actually a fall, I used these points to check that my model was working correctly. I then had to determine the effect of drag on Baumgartner's fall, as the net force acting on him included both the force of gravity and drag. However, after much trial and error, I found that the approximate force of air resistance was the best approximation of drag, as it allowed for the change in air density as well as a drag coefficient that I could change to tweak the model if necessary. However, it should be noted that the air density changed dramatically as Baumgartner fell, and the best possible way to incorporate this into the model was by taking the average over a set period of time. Nevertheless, the model I used was similar to that used in the Falling Objects lab, where the position and velocity data were updated using the momentum principle by using the initial conditions that were extracted from the official report of the jump. I then ran the model for about 5 minutes, where delta t was about 0.1 seconds, this was about the same time that Baumgartner fell before he deployed his parachute. And these are the results. The program outputted the velocity and position data at the times of 34 seconds, 50 seconds, 180, and 260 seconds. At 34 seconds in the actual jump, Baumgartner achieved the speed of sound, but the model predicted a velocity which is very close but actually less than the speed of sound. The other data points followed suit. The last two outputted data points at times 180 and 260 were dramatically less than the actual speeds that Baumgartner achieved, although the altitudes were the same. This may have been a result of the other forces that may have been acting on Baumgartner as he fell, which we don't really know about, and I was not able to model in the program. If we graph the predicted motion data and velocities, we see that both curves have sort of sharp curves, which are a result of the averaging of the air densities to accommodate the model, as if the model had gone on without these adjustments of the predicted motion predicted that Baumgartner would have hit the ground and gone straight through. If we compare the model's velocity with the graph of the actual velocity, we can see that both graphs have a sort of parabolic shape, and this shows that although the model averaged the air densities over time and had sharp curves, the motion was still predictable, slightly off from the model, but still predictable and in the same ballpark. Now, why is this important? Why do we need to be able to predict this kind of motion? Well, one reason is the parachute. If the parachute was opened too early, its slowing down effect would have not worked, but if it was opened too late, the stunt would have ended very badly. So when should Baumgartner deploy his parachute? The answer is around the time as he nears terminal velocity, as this is when the net force is equal to 0, meaning that all the forces acting on him as he falls are canceling each other out. This would allow the parachute to slow him down effectively, as it would be the only force that is uncancelled as he's falling. Another point of interest is the effect of temperature. How could the changing temperature as Baumgartner's falling affect the model prediction? Well, the answer is that the temper is actually already incorporated into the model, as the air density depends on temperature by the ideal gas law. So technically, the effective temperature was already accounted for, even though it was averaged into the model. But what about Baumgartner's body temperature? We all know that as objects enter the atmosphere, they begin to burn. And if we take Felix as our system and the air around him as the surroundings, we can calculate the decrease in Felix's body temperature, which would lead to, in turn, to the increase in the temperature of the air around him by using the energy principle. If we calculate the change in temperature just for the first 5 minutes, approximate 5 minutes, we can see that the increase in temperature around Baumgartner's body was approximately 100 degrees Celsius. So it was a good thing that he was wearing a pressure and temperature resistant spacesuit.